Thank you so much, and thank you all for being here today. My name is Rob Jackson. I'm an earth scientist at Stanford University and grateful for you being here. I'm grateful for the Asahi Glass Foundation for their support of the environment and the AGC Corporation as well for supporting the Blue Planet Prize. And before I start, I would just like to acknowledge the students and other lab members over the years who've helped me do all of the research that I'll talk about today, and it's only through their efforts that I've been able to do my work, and a few of them are in the audience, so I'm grateful to you. And I, of course, want to thank my family, my wife, and I have a son here who's just finished college in the room, so thank you all as well. I'll give you a little bit more background in a minute. But I'm here today to introduce the concept of restoring the atmosphere, and what I mean by that is that we're used to thinking about restoring forests, restoring wetlands, restoring endangered species to health, and I believe we need to apply that same concept, that same idea to the atmosphere. And what I mean is we have greenhouse gases that are at much higher concentrations than they were originally, and my hope is that we can restore the atmosphere to bring those concentrations back down to pre-industrial levels and reap a lot of benefits, not just for climate, but for health. And the gas that I focus on and will emphasize in the second half of my presentation today is methane, as you saw in the video. Well, I want to begin by just acknowledging that climate change is here. This isn't a topic for future generations. This is happening now. And 2023 was the hottest year on record until 2024 came along, and it shattered the previous year's record. And last year was the first time the Earth had ever been 1.5 degrees Celsius above pre-industrial levels. That's an occurrence that I never thought I would see in my lifetime. It's come much faster than we expected. And you see that in this plot here, the two high bars on the right represent 2023 and 2024. So climate change is here, and we are already paying the price for climate change through things like increased weather disasters. We all sort of have a sense that our weather's gone weird. And this is a picture that I took after a fire in Santa Rosa, California. This fire happened after a very, very wet winter that resulted in a lot of plant growth, and then a very record heat in the summer, so that all of that biomass dried out, and then a fire and winds came along and swept that fire through this neighborhood that you see, and you see the outcome of that here. So these are not just because of climate change, how we build houses matters too, but this fire was worsened by climate change and the drought that occurred from very, very hot temperatures that year. So we have a sense that these disasters are happening more often. They're many times more common today around the world and in my country of the United States. And in the US, we pay about $100 billion a year extra, more than we used to pay just a few decades ago, to help people rebuild after these disasters. So climate change is here as a physical phenomenon, and we are already paying for it today. Much of the work that I have done in the last couple of decades has been with a group called the Global Carbon Project. In the GCP, we track emissions of greenhouse gases that include carbon dioxide and methane, nitrous oxide, and we're looking at some new gases, hydrogen and others. We track the sources of these gases from nature, from oceans and land, and from human activities as well. We try and put all these pieces together to understand how much they're going up and why they're going up. I have some Global Carbon Project colleagues in the audience today, Pep Canadell, Prabir Patra, and I would just like to thank them and the whole GCP team for many, many years of work. One of our signature products is a yearly release of what we call the Global Carbon Budget. This is work led by Pierre Friedlingstein in the United Kingdom. And what you're looking at here is a trace of carbon dioxide emissions going back about 35 years to 1990. And you see that even today, carbon dioxide concentrations are still rising. They're still rising a little bit, not as fast as they were a couple of decades ago, but they're still rising. They're not even flat yet, and being flat isn't good enough. We need those emissions to be zero to stop the increase in the Earth's temperature. So we have a lot of work to do for carbon dioxide. And since sort of the first IPCC and Conference of the Parties for Climate Change, concentrations of carbon dioxide in the atmosphere have gone up by almost 2/3. So concentrations of all greenhouse gases are still rising, and we have to do something about that. So why is that? Why are carbon dioxide concentrations still going up when you know that we're building lots of wind and lots of solar and lots of renewables? So why hasn't that reduced carbon dioxide in our air yet? And the reason, there are a couple of reasons why it hasn't happened. One is visible on this graph. The fossil fuels here are on the left, coal, oil, and gas. The green bars that you see on the lower right, you see the very rapid rise in renewables. That's primarily solar power. And that's a remarkable transformation of the energy economy, something to be proud of, and something that happened faster than people expected. So it's a testament that societies can change and change the way we generate electricity and transport and things. But in spite of going up 10 or 11% a year, we haven't reduced fossil fuel use yet because we keep using more and more energy for, data centers and other things. So we add this additional renewable energy on top of the fossil fuels that we use already, and we don't take those fossil fuels offline. So that's one reason, is our insatiable appetite for more and more power and energy. But a second reason is that there are industries that are difficult to decarbonize. And the most difficult industries around the world are those that require furnaces to make steel, to make cement, that require you to heat things up to thousands of degrees. Perhaps this is true for glass as well. You have to heat furnaces up to thousands of degrees, and that takes coal in many cases. And these industries have been very difficult to decarbonize. I love photography. These are I'll show you some pictures from a steel plant in Sweden that I visited a couple of years ago. So this is sort of the old way of producing steel that you're looking at here. And inside that giant facility is a furnace like this that uses coal to generate the heat that melts the iron and everything that goes into making steel. So the old way of producing steel was this way, and this is the way we've made steel for well over 100 years. And really dating back even farther than that. And this is the new way of making steel. This is the first facility in the world to produce steel without any fossil fuels whatsoever. This is in Sweden. It's a partnership called Hybrid. And what's beautiful about this facility and this operation is that they make hydrogen on site using clean hydropower. So they produce a lot of hydrogen. They use it to raise the temperature of the furnaces up to thousands of degrees, and they have eliminated all coal use from their operations. So that's an example of a business transforming the way they make their product. But a take-home message here is this only happened because there was a price on carbon dioxide pollution, and Sweden and Finland were the first countries in the world to make companies pay to release greenhouse gases into the atmosphere like carbon dioxide. So because there was a price of about $60 a ton of carbon dioxide, avoiding paying that extra cost allowed the company to invest in a new way of producing their product. And now that product is better and may ultimately be even cheaper than the old way with coal. But it only happened because we priced greenhouse gas pollution, and we have a long ways to go to continue that today. So there are good things happening, and I want to remind you of that. But industry isn't the only thing that we need to think about in terms of climate solutions. I've been fortunate to do a lot of work in forests and grasslands and wetlands and ecosystems around the world in my career. And land, plants, trees primarily, absorb about 30% of all of the carbon dioxide pollution that we release into the air. And they do this for free. The trees grow a little bit faster because carbon dioxide is food for plants through photosynthesis. So they provide this service for us for free. And of course, forests do lots more for us than just absorb carbon dioxide. They purify our water, they clean our air, they hold on to our soil and make healthy soil. So there are a lot of reasons to support our forests and restore our forests beyond just the climate crisis. I continue to be fortunate to work in natural ecosystems as well as the built environment. This is a project in Sweden that we have. A colleague here, Kabir Pei, is a molecular fungal biologist. So we study fungi in the soil. And I would also acknowledge my colleague Anders Ahlström in Sweden, who's one of the leaders of this project. And we're studying old growth forests, so trying to understand how preserving our healthy, intact primary or old growth forests can not just help the climate, but help us grow plants more quickly and provide all of these other benefits that forests provide. So we're documenting the benefits of old growth forests in Scandinavia and in North America and other places around the world. So I just want to take a few minutes and describe some of the work that we're doing now to give you some insight into the things we do and the questions that we ask. And in Sweden, here we are sampling hundreds of old growth forests that as far as we know have never been logged or cut, but they grow in a matrix of industrial forestry, monoculture, heavily managed forests. So we're able to compare an old growth relic with an adjacent heavily industrialized forest plot next to it. So we can compare the trees and compare the soils right next to each other. And we do that in dozens of locations across Scandinavia. If we ask questions about how much extra carbon do old growth forests store, do they store more carbon, and what some of the other benefits might be. So we estimate the tree biomass comes from national forestry inventory plots. We don't have to cut down trees to do that. But we quantify how much carbon and the diversity of microbial communities in the soils of each of these plots. And these are photographs that you're seeing here. We're sampling the soils. We're measuring the carbon that's in the soil. We're using molecular tools to look at the DNA of the fungi that are present, the symbionts that grow together with the trees. And we analyze those and see if they're more diverse in these old growth forests than they are in industrial plantations. So let me just show you a couple videos of what these look like. For some reason it's not. What's that? Yeah, I need. How do you turn the pointer off? I click it again, will it go off? Okay, here we go. Sorry about that. So here you're looking down on top of one of these old growth forests. If you look closely, you'll see us kind of on our hands and knees there in the middle of the image. And these forests are beautiful. They have a rich understory. There are peats in many cases of these, and they are really beautiful places to work. So that's an example of an old growth forest from above. So let me just show you some things that we've learned by studying these forests. And that's the map on the left is where we've sampled. And the two bars on the right compare the old growth forest in the tall bar and the heavily managed forest in the lower bar. The light green parts are the carbon contained in the trees. So you see that old growth plots have more wood and more plant biomass than the industrialized forests. And that's not surprising really, because the industrialized forests are younger in general, and the old growth forests have had more time to grow. But what is really surprising in this plot are the large brown bars. Now let me go back to my. So these brown bars here, you see that the carbon contained in the soil, first of all, is nearly as much as the carbon contained in the trees for many of these plots. So that's another reason why we prioritize and value soil carbon so much. But you also notice that the soil carbon in these old growth forests are twice as high as the soil carbon in the managed industrialized forest, the difference between this brown bar here and this bar here. So we've somehow, by managing these forests intensively, we've lost the health of our soils. And one of the things that we try to understand is why is that? Why did that occur? And there are a couple of reasons why this might be the case. One is that in heavily managed forests, we tend to trench them when we plant. We mound, we plow, we disturb the soil, we break that soil apart, like the image that you see on the right here that I took, where a giant, almost like a knife, is used to cut the soil and break the rocks. And along this row, the seedlings are planted and have greater survival. So that's how we manage these plots in much of the world, including my home country of the United States. So let me show you what that looks like from above, and think about the difference between that and the old growth plot that I showed you a minute ago. So here's an image of a site that has recently been cut, and each of these rows that you see here looks almost like a road. Each of those rows is one of those blade cuts. And so you can imagine how disturbing that is to the soil. It chews the soil up, it makes it more available to microbes for decomposition. It disturbs the rock layer, it changes the way water flows into the soil. So this kind of practice happens all the time. It doesn't need to, and we can change the way we do industrial forestry to be less destructive as well. And then finally, the second possibility for why we've lost so much carbon is that the old growth forests have a much more diverse and a much richer group of symbionts, of mushrooms and fungi that live with the trees. And that's something that we're exploring now with my colleague, Kabir Pei. So these are some of the mushrooms that we sample there. And as I mentioned, we take soil samples, extract the DNA from those soil samples, and compare the diversity of fungi in these old growth and managed forests. And we do this for a couple of reasons. We're interested in the outcome, but we also hope to perhaps use this knowledge to improve restoration success. If you're growing trees somewhere else, it might help to transplant some of those mycorrhizal symbionts that have been lost. And it may help the trees grow faster. So there are both basic science and applied applications for this knowledge. And then finally, before I turn to methane, I do also work in peatlands. So most peatlands are very far to the north, in the Arctic or in boreal forests. And many peatlands have been lost, and we're worried about peatlands losing carbon to the atmosphere as they warm. They have thousands of years of plant photosynthesis that's built up in the soil. In many cases, that carbon is frozen, and as the earth warms, that carbon becomes available. Microbes go to work on it, they eat that carbon and then release either carbon dioxide or methane. And we're worried about accelerating climate change as we warm the earth. And so I am fortunate to work in these systems and to work on peatland restoration as well. And peatland, it can be a source of methane, as you heard about in the video, and I want to turn for the rest of my talk to focus on methane and why I spend so much of my current research on that particular greenhouse gas. Well, first of all, methane concentrations have been rising faster than at any time in the last 5 years, and we're still trying to understand exactly why that is. So methane's going up a lot. It's going up faster than carbon dioxide is. And I focus on methane because it's extremely potent, far stronger than carbon dioxide, and because it's shorter lived. That combination, potency and short lifetime, means if we could reduce emissions, we could shave or reduce peak temperatures in the atmosphere within the next 10 or 20 years. And methane is the only greenhouse gas for which that's possible. Carbon dioxide is the most important greenhouse gas long term, but methane is the best lever we have for slowing climate change in the next few years. And that's why I work on it. And an illustration of the concept of what I mean by atmospheric restoration here, this is an image of methane in the pre-industrial region. You see it was relatively flat with a little bit of noise, but then you see the rise from industrial activity. And to restore the atmosphere for a gas is to bring that high concentration back down to where it used to be. And my dream currently as a scientist is to restore the atmosphere for methane, to bring those concentrations back down to where they were. Doing so would save us 0.5 degree Celsius of warming in a short period of time. It would save hundreds of thousands of lives because all of that extra methane we release into the atmosphere results in more ozone that we breathe. And ozone is a gas that kills us down close to the earth. There's good ozone up high and bad ozone here near the earth. So I want to spend the rest of my talk focusing on how to and where to reduce methane emissions. This is a plot of our global methane budget. It's a little hard to see on the screen. The bar on the left is the amount of methane that goes into the atmosphere from energy use, natural gas use, and oil extraction, for instance. And that's about 100 million tons a year. The bigger bar next to that is the methane that goes into the air from agricultural activities, primarily cows that burp, producing rice. Those emissions are harder to lower than the energy sector, so I spend most of my time now thinking about ways to reduce methane emissions in producing and using energy. But really, any bar on this is a place that we could make a difference. Wetlands, the bar that's hatched and in the middle, that's the largest source of methane from nature. So we also, in my lab, work a lot in wetlands. And for wetlands, tropical wetlands are the part of the world that release the most methane. And for those of you who may not know, methane is produced in warm, wet, low oxygen environments. So in a swamp, in a rice paddy where there's not much oxygen, the stomach of a cow is like a walking wetland. It has a stomach that has moisture and it sloshes around, and microbes that live in that environment release methane, and the cow burps that methane to the air. So we focus on tropical wetlands because they're the largest natural source, and because there's evidence that they're already starting to go up, the emissions in places like the Congo and the Amazon and here in Southeast Asia because of the warming of the earth. So there's already some warning signs happening in these ecosystems. This figure just shows you one of our new research sites in Brazil at the Mamiroa Sustainable Development Reserve. That figure on the right is a new tower that we just built that monitors methane and carbon dioxide emissions at this location with our partners there. We work with partners in Peru, Brazil, and French Guiana, and all across the Amazon and into Africa to do this work. And all the people you see along the bottom of this slide are our local experts who we partner with and are critical to all of this work. So a thanks to them. But one of the nice things about my job is that when I go to do my science, I also get to take photographs of jaguars and giant river otters and see wildlife around me. And that's a source of pleasure in my life. What you're seeing here is, this is an Amazon, some instruments we're setting up in trees on the right. And then the new sites that we're building are in red, the red dots that you see in this map. And all the blue dots are where we currently can monitor methane from towers around the world. And what you see from this graph is how little we know about the tropics and how few observation stations that we have there. And that's why this is one of our current areas of focus. And these are the people that are helping us in each country. I already mentioned the vulnerability of wetlands, and this is an example that was very recent. In the last El Nino in 2023 and 2024, last year more than 20 million hectares of Amazon forest burned because of a record drought that occurred associated with the El Nino. Levels of water in the Amazon were the lowest we had ever seen over more than a century of monitoring. So not only was there not much water in the river system, but the water that was there was so hot that the river dolphins literally died because it was too hot for them. Temperatures got to 40 degrees C in the water, and they just couldn't survive through that. So we're already seeing changes in even the most remote places in Earth today. So let me switch. For the rest of my talk, I mentioned that I work a lot in the energy sector. I want to provide you some examples of things that we can do. How can we make a difference today and in the next few years to help solve this problem? And I'll show you some examples of that work. When I'm not in places like the Amazon, where I love to be, I'm in helicopters. We fly and film leaks from oil and gas wells. We put sensors in cars and drive around cities and look for leaks. We put sensors on top of skyscrapers in cities like Tokyo, in this case in Boston, and measure the concentrations of greenhouse gases in the air in those cities and try and understand from what sources pollution comes. And we work in homes and buildings to quantify emissions too. Here's an image of I call this a restaurant inspection. We use special cameras that allow us to film which facilities are leaking pollution to the air, in this case methane. So this is a helicopter shot from an oil and gas field in Texas. And you see as this comes on, you'll see the image from the helicopter. We'll sweep across the oil and gas pad. That plume that you see is methane and other pollutants, hydrocarbons leaking into the air. That plume is invisible to the naked eye. If you drove along that road, you couldn't see it. So you have to have a special infrared camera to find this. And you can imagine how if the wind changed direction in this picture, if it changed direction, it might waft that plume of pollution across the house at the top of the screen, and the people in that house would breathe what's in that gas. So we can use special imaging to find these kinds of leaks more quickly and help get them solved, to work with companies and regulators to help fix the problem. So this is kind of the old way of doing it through helicopters and planes. The new way of doing it is really, really exciting, and that's that there are satellites now that can do this from space. These images are from the Carbon Mapper satellite. It's an oil and gas well on the left and a landfill in Pakistan on the right. And each of these plumes that you see is a point source, a super emitter of a methane, and that plume is released from that site and blown away from it with the wind, and you're looking down on top of that from the sky. These new satellites, and Japan has some satellites like GOSAT that you've launched here. Each of these satellites allows us to zoom in and see what are the sources of this pollution, who owns them, and if you can get that information quickly, you can act on that information quickly and get those emissions stopped. And less than sort of 1% of facilities in an oil and gas field cause half the pollution. So it really makes sense for us to find these quickly and get them put out. And you don't need permission to have a satellite, right? I can't fly into Russia in a helicopter. I can't fly across China or Azerbaijan, but you can look anywhere in the world with a satellite and see what's happening. Another example of our work is pipeline leaks. So we did the first studies, in this case with my colleague Nathan Phillips in Boston. And what you're seeing here, this is literally the city of Boston from above. The red lines are the roads that we drove in Boston. And you can imagine in a car, we had a special methane analyzer in back. So everywhere we drove and we sniffed a leak, the instrument would tell us there's a leak here. And each of the leaks of methane in that city is the gold bars that you see. So we found more than 3,000 leaks across Boston, about four leaks for every mile. And the number one predictor of a methane or natural gas leak in the city was old infrastructure, old pipes, some of them more than a century old. Your cities here tend to be newer, so I wouldn't expect you to have the same number or density of leaks that we have in old cities, but we can do better than this, especially in one of the richest countries on Earth. And sometimes the nice thing about being a scientist is that your work can catalyze the work that many people have done over decades, and that was the case for us in these images. That image, when we published our paper, was commented on immediately by the mayor of Boston, by the congressperson of Boston, who wrote letters to the agencies responsible for these leaks and said, we've got to do something about this. It isn't just a climate change problem, this is a safety problem. Every one of those yellow spots is a potential source of explosion. So within a year of publishing that paper, Massachusetts passed a new law to repair and replace these leaky pipelines, and we were able to help get some of those fixed. Same thing happened in Washington, D.C. We mapped more than 6,000 leaks. Here you're looking at Capitol Hill on the left, another old neighborhood, and the map on the right, each of those points, again, is a methane leak. Washington, D.C. Also passed, the Public Utilities Commission passed an accelerated pipeline repair and replacement bill the year after we produced these data. So once in a while, an image or science can provide information in a way that helps society see a problem and ultimately to help fix that problem. I want to finish by coming closer to home, and that is literally our homes. You have very high natural gas stove use. In Japan, we have quite high gas stove use in the United States. And we have several ways that we can reduce methane emissions ourselves. So what can you and I do individually? Well, we can switch from gas to electricity inside our homes. We can eat a more vegetarian diet, less beef because of the emissions from cows, and we can waste less food. All of those things result in methane going to the atmosphere. But I focus a lot on the pollution that comes from burning natural gas inside a home. And an analogy I use for this is that you would never stand over the tailpipe of a car just willingly breathe in the pollution from your car. But we stand over a gas stove and breathe in that pollution day after day, and it's the same pollutants that cars release, only our stoves have no catalytic converters to destroy that pollution. So a gas stove produces benzene, asthma-triggering NOx gases, and electric appliances like induction produce none. So by switching fuels in our home, we help climate and breathe less pollution indoors. And this is just a trace of, this is NOx, an asthma-triggering gas. These are 6 homes, and these plumes are how concentrations of that pollutant rise in the home after someone turns the stove on. And what you see is that in 3 of the homes, the concentration of the pollutant rises above the outdoor standard for that pollutant and stays there for hours. So that black line is what the Environmental Protection Agency says we shouldn't allow concentrations to go above in the air outdoors, and it appears indoors regularly for the people living in these homes. So again, switching fuels to cleaner energy will make us healthier in our homes and buildings. We work with environmental justice groups to try and promote this change in lower income communities for poorer people. And we just worked in an apartment building where they replaced all of their gas appliances with cleaner electric. And we monitored the change in air quality in about 15 of these apartments. And this is the kind of picture that you see there. The first week on the left is when the gas stove was in the home. And you see those very, very high spikes. The second week is after that gas stove had been replaced with a cleaner induction stove. And you see the elimination of all of that pollution. So this area of research is why first of all, I'm grateful to the Blue Planet Prize for the prize and for the funds that come with it. But I'm going to give my funds to Stanford University, and Stanford will match those funds. And we're going to create a new program in what I call Electrification for Health that targets people in lower income communities and tries to improve their indoor air quality. So I'm excited about this and grateful for the opportunity to do it. So let me just finish then with what I think is perhaps the most important take-home message. One of those messages is that climate change is here. I mean, it's not too late to do something about climate change, but acting on climate change and using clean energy won't just help the climate problem, it will save lives and make us healthier. I mean, as you can see on this slide, worldwide, 1 in 5 deaths still comes because of burning fossil fuels from particulate matter, and coal is the worst actor. So, that's 10 million people a year die because we continue to burn fossil fuels around the world when we no longer need to. And as I've said, climate action will make us healthier, and there are lots of examples of things where we've done the right thing, helped the environment, and saved lives and made us healthier too. Japan was the very first country in the world to recognize the threat that lead and gasoline posed, particularly to our children. So Japan banned lead and gasoline. Now every country in the world has banned lead and gasoline, and blood levels of lead have dropped 96%, saving the world trillions of dollars in health costs, literally making our kids smarter because lead pollution lowers IQ as children grow up. So that's a problem that we fixed. The world fixed, or is fixing, the ozone hole through the Montreal Protocol, the greatest environmental agreement that was ever signed. And then in my home country of the United States, we have the bipartisan Clean Air Act, where we recognize the benefits of reducing pollution, and that act still saves 100,000 lives a year in the US at a 30-fold return on investment. So every dollar that we spend on clean energy results in $30 that we save through healthcare and other things. So it's an economic reason to do this as well as a climate reason. So this is my dream as a scientist now, to restore the atmosphere for methane, to bring its concentrations back down to pre-industrial levels in the next 10 or 20 years, ideally. Doing so will save us half a degree C of warming, save hundreds of thousands of deaths from ozone pollution, and provide a narrative of success. So that's my message for today. Thank you for your attention, and thank you to the Blue Planet Group for everything.